This is project 5, video number 1, the one in which we do the pencil and paper part of the project. We got a meter stick. It's supported by a pin at one end. And a piece of string that extends from a point directly above the pin right here to a point on the meter stick. I think I'll put it not quite so close to the middle there, at a distance X from the pin. So and it is at a height H equals 0.5 meters above the pin. There the upper end of the string is. Distance H over there. Okay, so I'm gonna call that theta. I'm gonna call this L for the length of the string. And L from Pythagorean's theorem is square root of h squared plus x squared. Now I need a free body diagram. So what we're supposed to do is graph the tension in the string versus the position x from x is equal to 0.01 meters up to 1.0 meters. So our perfectly straight meter stick. I'm going to call the pin P, or the point at which the pin is attached, point P. So call it that point is point P. They call this FPY, FPX. We got at X, we got a force I'll call F sub T for the tension in the string. Let's see if I can indicate that that's at a distance X. Yeah, then it doesn't look like this really labels that vector up there, so let's see if I can fix that. F PX. Alright, here's FPX. We got the gravitational force acting down right at the center. F sub G. I choose to change the name of this to R. I think that's the only place I got it so far, because I want to call the length of the stick L. And I'll make this distance be L over 2. So I changed my mind on the name of, I'll call it a variable, even though it's a constant, the length of the string from, I was calling it L, but I'm going to call it R, and then the length of the stick I'm going to call it L, which is 1 meter. Alright, I got one vector up at an angle, so I got to do a vector component diagram with it, for it. So there's FT. I'm going to use a coordinate system in which X is to the right and Y is up. So this is X component vector is in the minus X direction, so I'm going to label it with its magnitude, which is the absolute value of the X component of the tension. The X component of the tension is actually negative. Then this one's positive, FTY. This is theta. So we have FTX is FT cosine theta. Yeah, didn't leave much room there. Try it again. FTX, absolute value sign, equals FT cosine theta. And that's equal to, let's see, the cosine of theta up here from this diagram, cosine of theta is equal to X over R, and the sine of theta is equal to H over R. That's from our sketch, by analyzing the triangle in the sketch. So this becomes FT times H over R. And then FTY is equal to FT sine theta. I don't think I'm going to need that, but might as well be complete here. FTY is this. FT times H over R. And since that's the same thing I got up there, this one must be wrong. Cosine of theta is X over R. Alright, so let's redo the free body diagram, but with FT being replaced by its components. FPY, by the way, this is point P right here. Point P. FPX. Ooh, that's the one that I want to get rid of, so FTY. And I chose to put this one leftward rather than having it turn out with a minus sign. I knew it was leftward, and that's ftx absolute value. I think it'll save me a little bit of time if I put down what that is. That's fty was ft h over r. ft times h over r, then we've got fg acted down. And let's get the distances on there. This is x. I think put this equals mg. And the ruler mass was given as 112 grams, so 0.112 kilograms. And I want to put that distance on there as L over 2. So I think I'm ready to analyze this free body diagram. And all they want is the tension. They don't want fpx and fpy. So the easy way to make it so that they don't appear in the equation is to sum the torques about point P. Then those two forces go right through the axis of rotation, and they don't contribute to the torque. So sum of the torques about point P, I'll call counterclockwise positive, is equal to 0 if this thing is in equilibrium, and it was given that it is in equilibrium. So we've got ft y, or right off the free body diagram, as long as it's on the free body diagram I can take it, ft times h over r times x, so it's moment arm, and then minus, this one's tended to rotate things around clockwise, and I call it counterclockwise positive, so minus mg times L over 2 is equal to 0. So ft is just mglr over 2hx. Okay, so I could substitute for the r being h squared plus x squared. Normally I wouldn't do that, but it's already complicated enough. So I think I will in this case. Is equal to mgl h squared plus x squared square root all divided by 2hx. And I choose to take the h and the x inside there, in which case they become squared inside the square root. So I'm going to write this as 0.5 mgl times the square root of, inside the square root these become squared, so it's h squared over h squared x squared, which is just 1 over x squared, plus 1 over h squared. And that's the ft. See if that makes sense. This is a force mg all by itself, just the gravitation force acting on the meter stick, and then L times something that's going to have units of 1 over length, so that last part there, after the G, everything is unitless, so it does come out in units of force. So I think I'll just go ahead and use that. I'm supposed to evaluate this at x is equal to 0.75 meters. So at x is equal to 0.75 meters, ft is equal to 0.5 times 0.112 kilograms times 9.80 newtons per kilogram times 1.0 meters, and then times the square root of 1 over 0.75 meters squared plus 1 over 0.5 is how high the tie-off point was above the meter sec squared. So plug that into a calculator and I get 1.31915 newtons. And that's only good to 3 sig figs, so all of that is uncertain. Alrighty. Let's see what we got to do for the code. So I'll call this the code outline. So initialize variables. I think I might actually be able to see all the ones I need right here. M equals 0.112. That's how many kilograms M corresponds to. G equals 9.8. L equals 1.0 meters. I'll go ahead and put down, even though what they are, the units are, even though they're not going to appear in the code. Meter, and then X and H. I guess H equals 0.5 meters, but X will go, I'm graphing versus X, so I use linspace to fill up X, let X be an array of a bunch of values, so linspace from 0.01 to 1, and let's go with 100 values. If that doesn't look smooth, I just bump that up. And then I'll be analyzing this thing. I think I'll try to make it as a MATLAB statement. 0.5 times MGL. So F T, I think I'll call it, equals 0.5 times M times G times the square root of X I'm going to use the dot there to say squared on an element by element basis, plus H squared. and that was 1/ that and a 1/ that. That didn't turn out too well, so let's so 1/x dot. Oh, I think I need ./ there. So 'let's see if I got that copied down right. With 0.5 mgl. So I need times L in there. I could put it afterwards, but I think I'd rather fix it up. 0.5 mgl. .5 mgl times, oh, and I forgot the 1/, again. So plus 1/. So I guess I'm not sure that the square root will work on that whole thing, but this creates an array. This adds a number to each element of the array, and then I try taking the square root of the resulting array, and then I don't need .* here. Just the asterisk will do, because all of these are just numbers. So I'm multiplying a number times an array as opposed to trying to multiply two arrays. So then I'll do plot x comma ft, and that should do it. Yeah, all I had to do is that. If they'd have asked for FPY, or the force of the pin, for instance, then I would have had to do some of the forces, but didn't have to worry about that this time. Alright. Okay, I think I'm good. Let's call this a wrap for Project 5, the video number 1.